6.3, the sampling distribution of x bar and the central limit theorem. So if we have the sample mean, remember that's x bar, and this mean is for your population, and we want to take a large number of samples and find the average x bar. Okay, so if we're looking at just a scenario, say the wait time for the students waiting for their parents to pick them up, we are going to take a whole bunch of samples of size 10 or size 20 or size 30 and a whole bunch of those samples, and then look at the distribution of the mean wait time for those, and that gives you a much better idea of what your actual wait time is. And we're going to do this theoretically. That's what we're working on right now, because then we'll actually apply what we've learned from this to actual statistical analyses. So we have this idea of a minimum variance unbiased estimator. Now we know about that. We've talked about it in the last unit, that if we're trying to find a good estimate, we want the one that's unbiased. It has the same middle point as our population middle, and we want the one that has the smallest spread or the smallest variance. So we just put it in a little bit different order and call it minimum variance unbiased estimator. So yeah, we want to know which measure gives us the, oh my goodness, an unbiased estimator with the smallest variance. Okay, so suppose a population has a uniform distribution, and so we have a picture of it here, and it looks like our function is 1/50, and then the mean and the standard deviation of the population are going to be, it looks like halfway between 150 and 200 is going to be 175, so that's going to be our mean. And our standard deviation is going to be 14.43. Okay, now suppose that we take a sample of 11 measurements from this population. So this population has this distribution, we know it's a uniform distribution, and we're going to take 11 measurements from that population. So we're grabbing 11 randomly selected measurements, and we want to describe the sampling distribution of the sample mean x bar based on 1,000 of those experiments. Okay, so here's what it'll look like. Here's where all the x bars are going to fall. So we're looking at a bunch, 1,000 experiments, and we're looking at where did the mean fall for each of those experiments. We expected it to be this uniform distribution where our mean was 175. And so we're looking at just the mean for all of our little samples, and here's where all the means fell. And the means actually look pretty normally distributed. And we did 1,000 experiments, so that was a lot, but we have a mean right here real close. There's 175 right there. It looks like it's right tip top in the center of there. And so that's the point, is that the more samples that we take, the closer the distribution of all the means that we collect, the closer that is to our actual mean. So when we look at that, and we're not going to do this in reality, but theoretically we like to think about it because we want to know how close can we get. So here's the properties of this sampling distribution of x bar. So back here, remember, this is what we're doing. We take 11 measurements from the population, and we calculate the mean. Then we write that down. Then we take 11 different measurements from our population, calculate the mean, and write that down. And we do that a total of 1,000 times. So we're looking at a whole bunch of different 11 measurement samples and writing down all the means from all of them and then putting them into a histogram. So the histogram is just of the means that we collected from 1,000 experiments, and it's showing us the average mean for all of our 1,000 samples that we collected. Okay, so the mean of a sampling distribution of X bar equals the mean of the sampled population. And this is important. This is the properties of a sampling distribution of X bar. This is hugely important because what we're saying is if we take a whole bunch of samples, that mean of the X bar that we get is going to be the mean of our population. So the mean of our X bars is going to be our expected value of X bar, which is going to be our population mean. So that's a huge earth-shattering revelation that if we did enough experiments and with our samples and did a distribution of all the X bars or the averages from each sample, then the middle of that distribution is going to be the same as our population mean. And that's fantastic to know. Anyway, for me. Okay, so the standard deviation of the sampling distribution of X bar is going to be the standard deviation of the sampled population divided by the square root of the sample size. Now that's something we haven't seen yet, and it looks just like this, that if we're looking at the standard deviation of X bar, and that's for, remember, where we're looking for our population mean, then that standard deviation where we're looking for our population mean is going to be the standard deviation of our sample divided by the square root of n. So I'll write that sideways how we're used to seeing it. And this standard deviation we also call the standard error. So that's the same thing as our standard error. So we look at those as synonymous, but we are dividing our population standard deviation by our square root of our n. So the bigger the n is, and we'll look at this here in a second, our approximation to our mean for the X bar was precise in example 6.6. I think that's the one that we just did back here. Way back, maybe. Yeah, right here. This example where we found our expected value and they came out equal, it's not a big surprise. We wanted you to see that in this example, and this was at the end of 6.1 where they came out both to 2.7. And what we're saying now is that guess what? You can expect that every time. So let's come back. So it was precise. Property 1 assures us it's going to happen every time. Property 2 tells us how to calculate the standard deviation of the sampling distribution of that X bar. So we had a 14.43 for our standard deviation in that example that we were talking about, and that was that uniform distribution for the sample. And our sample size was n equals 11. Remember, we did 11 items in each sample, and we did that 1,000 times. So the 11 is the number that we need to use. And so we put that into the denominator under the square root, and we get 4.35. So what we're saying is that the approximation that we got, in example 6.6 was 4.38. It's very close to the exact value of 4.35. And this value of the variance is the smallest variance among all the unbiased estimators. So X bar is going to be the closest. It's the, what does that stand for again? Minimum variance unbiased estimator for mu. So X bar is as good as you can get, and so we're going to use that. So if a random sample of n observations is selected from a population with a normal distribution, then the sampling distribution of X bar will be a normal distribution. So if our population, and our example was rectangular, so we'll have to look at that in a minute, but if our population has a normal distribution, then we're saying that X bar's distribution will also be normal. Okay, that's theorem 6.1. And then theorem 6.2 is the central limit theorem. And it says, consider a random sample of n observations selected from a population, and that could have any shape. So that could be skewed, irregular, etc. We don't care. And you have some mean and some standard deviation. And then we say if n is sufficiently large, the sampling distribution of X bar will be approximately a normal distribution with the means equal and the standard deviations following that formula that we just gave, where you take the standard deviation of the population divided by the square root of the size of your sample. So, and here's the caveat that's important to us. The larger the sample size, the better will be the normal approximation to the sampling distribution of X bar. And that crossed it out for me. Thus, for sufficiently large samples, the sampling distribution of X bar is approximately normal. That's perfect. That's what we want to know right there. So if you wrote this down, circle it, underline it, whatever you need to do, if we get a large enough sample, then that distribution for our X bar is going to be approximately normal. And the beauty of that is then we can use all of those probability things to figure out the area under the curve. We can use our chart. We can use all that analysis that we've learned and make conclusions about our X bar using the normal distribution, which is fantastic. So how large must the sample size be so the normal distribution provides a good approximation? The answer depends on the shape of the distribution of the sampled population, and as shown in figure 6.1, which I think we don't have. Generally speaking, the greater the skewness of the sampled population distribution, the larger the sample size must be before you have a normal distribution. So for most sample populations, sample sizes of n is greater than or equal 30 will suffice. So it's not that big, but you have to have at least 30 in your sample for you to have the assumption of a normal distribution for your X bars. And here's the chart that was discussed there. There it is. So what we're going to say then is, write it down here, magic number n is greater than or equal 30 assures an approximately normal distribution for X bars sampling regardless of the distribution for the population. Okay, so that's pretty exciting. That's pretty exciting. And okay, maybe just for me. Okay, so let's take a look at this. So here's the original population. So the shape of the population, this is like the example we started the lesson with. This one is uniform. And what we find is if we have n equals 2, that our sampling distribution looks like a triangle. And if we have n equals 5, all of a sudden it looks pretty mound-shaped or normal. And if we go up to n equals 30, remember that's our magic number, then it's a definitely normal distribution and our spread is very small. If we look at the original population being irregular, when we find our sampling distribution of x bar for two people or things in our sample size, then here's the shape of our x bar sampling distribution, not so great, but once we get to n equals 5, it's looking pretty much like a mound shaped, and by n equals 30, it's very much mound shaped. This one you could kind of call skewed right, but it's again irregular. And when you look at the sampling distribution of your x bar, it's going to be skewed right if your n equals 2. And here it's starting to look pretty normal, but still slightly skewed right. And by here, by n equals 30, we're looking at a normal distribution for our x bar's sampling distribution. Okay, down here, if we start off uniform, it's going to, we start off normal. For the original population, it'll be normal, 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 all through for all the sampling distributions. So that one is what we started off our first theorem, and then the other theorem said for any shape, as long as you get to n equals 30, you're pretty much guaranteed a normal distribution for your sampling distribution for your x bar. Okay. All right. So some comments about that sampling distribution of x bar. This formula, the sigma for x bar, you can see the sigma and then you can see the x bar. So we're talking about the sampling distribution of x bar and what's the sigma for it. It's going to be the sigma for the population over the square root of n. The standard deviation of the sampling distribution x bar decreases as the sample size n increases. So here's a real example. If your sigma is 6 and your n is 50, then your sigma for your x bar is going to be 6 over the square root of 50, which comes out to 0.85. Okay, if we double that and we use an n of 100, then our sigma for our x bar is going to be 6 over square root of 100, or 6 over 10, which is 0.6. So our sigma for our x bar is getting smaller, and that's good. Remember, smaller means it's tighter packed around the actual mean, and so that means you have a lot less variance, a lot less variability in your values that you're coming up with. So this relationship holds true for most of the statistics that we're going to look at. The central limit theorem, so here's a refresher, provides a useful approximation of the sampling distribution of the sample mean. And it explains why many relative frequency distributions of data have mound-shaped distributions. So if we're looking at a relative frequency distribution, and it could be just the original data from our sample, sometimes that's already a mean or a sum. And for example, the monthly demand of blood at the hospital, we're looking at how much, or the sum of how much each patient needed in a month, and so it's already a sum, and then we're doing a distribution of the sums of everybody, and so that makes it more mound shaped because it's the sum of sums kind of thing. So sum of averages. Okay. So we don't want to spend a whole lot of time on that idea, but when we're talking about data that is not just a single answer to a question, but it's actually a total for a person, like how much water you drink in a day, that's going to be a sum for each person, and so then when you find the mean of that, it should be pretty normally distributed. Okay, let's look at this problem and see what we can figure out. And this is really going to bring home the idea of this different size samples giving you a better measure of the standard deviation. So suppose a random sample of n measurements is selected from a population with a mean of mu equals 100 and a variance of sigma squared equals 100. For each of the following values of n, give the mean and standard deviation of the sampling distribution of the sample mean x bar. Now this is giving us the sigma squared, and we really want sigma, which is the square root, so it's going to be 10. So our sigma is 10, that's our standard deviation, so we're going to use that. So part A, we have n equals 4, so we know that our mean for our x bars is going to be the same as the mean for our population, so the mean is going to be 100, and the sigma for our x bar is going to be the sigma for the population, which is 10, divided by the square root of n, which is 4, and so that's 4, square root of 4 is 2, so 10 divided by 2 is 5. So for a mean for our x bar is 100, same as our population. Sigma for our x bar is 5, which is half of what our sigma was for our original population. Okay, part B. If the same situation but our n equals 25, our mean for our x bar is still going to be 100 because it matches the population, and then our sigma for our x bar is going to be 10 again over square root of 25. Square root of 25 is 5, so 10 divided by 5 will give me 2. And now I'm way down. I had a 5 for the first one with my n equals 4, and for n equals 25 now I have a sigma for my x bar, my distribution of my x bars is 2. So it's gone way tighter as soon as I increased my sample size a little bit. So let's look at C. So here I have n equals 100. So here my mu of my x bar, my mean is still 100, and my sigma for my x bar is going to be 10 divided by the square root of 100, which is 10 divided by 10, which is 1. Wow, I've gotten, with n equals 100, now I have a standard deviation of 1. That's fantastic. Let's look at part D. N equals 50. I might need my calculator on this one. Mean of x bar, still 100. Sigma of x bar is going to be 10 divided by the square root of 50. And I'll take the square root of 50 on my calculator. On my calculator, I can just say 10 divided by, and then I can type in the square root symbol, and then type in the 50, parentheses, and then enter, and it looks like it's a square root of 2, so it's 1.414. Oh, yeah, 10 divided by, oh yeah, my sample size went down, my n went down. I was wondering why it wasn't a better number for my standard deviation. So okay, let's look at part E. So this one, n equals 500. My mu of my x bar is still 100. Standard deviation of x bar is 10, again divided by the square root of 500. So I'm going to type in 10 divided by, and you might be able to type in 500 and then square root depending on your calculator. Mine, I need to do square root and then 500 parentheses, and then I get 0.447. And it's getting small, isn't it? Now let's check what happens if I have n equals 1000. My mu of my x bar is still my population mean of 100, and my sigma of x bar is going to be my population sigma divided by the square root of n. So divided by 1000, square root of 1000. So I'll do 10 divided by square root of 1000, parentheses, and I get 0.316. So my sigma of x bar equals 0.316. So I have a few answers here I need to box up. Just make sure that I've done that properly, so your worksheets will look done properly as well. and you can put just the equals sigma x bar off the end, so it's right there by our number. And so on. All right, let's take a look at another example. And this is a random sample of n equals 64 observations drawn from a population with a mean of 20. So mean is 20, and a standard deviation, so it's not variance this time, standard deviation of 16. Give the mean and standard deviation of the repeated sampling distribution of x bar. So that means we're doing a whole bunch of experiments, and our sample size is 64, but we're doing like maybe 1,000 of them, who knows how many. So let's look at A. So our sampling distribution, our mean for our x bar is going to be the same as the mean for our population, so it's 20. And then the standard deviation for our x bar is going to be our standard deviation for our population divided by the square root of our number of observations, or n, and that's 64, so it's going to be 16 divided by 8, or 2, for our sigma for our x bar. Box that up. That's part A. Part B, describe the shape of the sampling distribution of x bar. So remember, when we're thinking about the shape, we have to think about our magic number, and remember for that our n had to be greater than equal or equal 30. And we have 64. So the shape of the sampling distribution of x bar is approximately normal because n is greater than or equal 30. Okay, part C. Does your answer depend on the sample size? Yes, and that's our answer right there, because the sample size is greater than or equal 30. Part C, calculate the standard normal z-score corresponding to a value of x bar equals 16. So if my x bar equals 16, then my z-score is going to be 16 minus my mu, which is 20, over 2, which is my standard deviation for my sample. So I use my mu of x, which happens to also be my population mu, and then the sigma of x bar. So I'm going to use those two when I calculate z-score. So 16 minus 20 is negative 4 over 2, which is going to be negative 2. So my z is negative 2. Okay, so that's kind of important to remember to do that. Use your sampling distribution data for your x bar. Then calculate the standard normal z-score corresponding to x bar equals 23. So the z for this one would be 23 minus 20 over 2, so it'll be 3 over 2, so my z equals 1.5, and it's a positive. Good. And then find the probability that x is less than 16, x bar. So the probability, that's part E, probability that x bar is less than 16. If I draw a quick diagram, and boy is that one quick, I have 0, and my 16 was at, I did an x bar equals 16, that was negative 2, and I wanted to know less than that, so let's change colors here. So we're talking about all this here. And to find that, remember, I will need to find this entire region here, which is 0.5, minus this little region here, which I need to look up. And when I look that one up, I get, so it's going to be the probability, it'll be 0.5 minus the probability that x is equal to -2. And when I look that up, I get 0.5 minus 0.4772, which equals 0.0228. So the probability that x bar is less than 16 equals 0.0228. .0228. Okay, so let's take a look at F. Find the probability that x bar is greater than 23. X bar is greater than 23. And remember, if we make a little quick diagram, 1, 2, 3. There's my 0, and I know that I had a 1.5 for my z of my x bar of 23. My z is 1.5. So if I draw that in, that would be right about here, 1.5. And I want to know the probability that we're greater, so we're going off to the end. Back to the drawing board here. That means I have to again find the distance from here to here and subtract off the distance from here to here. So I know that one's 0.5. So it's going to be 0.5 minus, and when I look up the probability that x bar, and it's actually z now. I wrote that wrong on the last problem. Let me fix that too. So up here I was looking for the probability that z is a -2, and here I'm looking for the probability that z is 1.5. Okay, and so when I look that one up, 0.5 minus 0.4332, then I get 0.0668 equals, I can say, the probability that x bar is greater than 23 equals 0.0668. And then part G, find the probability that 16 is less than x bar is less than 23. Well, that was nice. They let us use the same numbers over and over, so we don't have a whole lot extra to do. Let's just draw our picture real quick. And we know we have 0 here, and we know we want it to be in between -2 and 1.5, so we're looking at all of this area here. So we've already looked up some of those values, so we can just reuse some things. But we know this should be the probability that z equals -2 plus the probability that z equals 1.5. And we have those two. It's 0.4772 from above plus 0.4332 from above. When we add those two together, we get 0.9104. And so we can say the probability that 16 is less than x bar is less than 23 equals 0.9104, which is most of our area here. So we're not surprised that it's pretty close to 1. Okay, so there's those. And now we have this phishing attack with a PH. Okay, phishing attacks to email accounts. Phishing describes an attempt to extract personal or financial information from unsuspecting people through a fraudulent email, which usually is full of misspellings and is way too good to be true. Data from an actual phishing attack against an organization were presented in the Chance Journal, and the inter-arrival times, i.e. the time difference in seconds, for 267 fraud box email notifications were recorded and are saved in the phishing file. You can go look at it if you're interested. For this exercise, consider these inter-arrival times to represent the population of interest. So we're just thinking about that as our population. Use the histogram of the phishing data below. Describe the population of the inter-arrival times. So if I'm looking at this histogram, it looks like it is skewed right. Histogram is skewed right because the tail is to the right. Okay, the mean and standard deviation of the population are given in the table below. Consider a random sample of n equals 40 inter-arrival times selected from this population. Describe the shape of the sampling distribution of X bar, the sample mean. And then theoretically, what are these two values? So the shape of the sampling distribution of X bar is approximately normal. And why is that? Because n is greater than or equal 30. That's all we have to know. N is greater than or equal to 30, and then your distribution for your X bar is going to be approximately normal. It's a wonderful thing. Now let's look at the other two parts. So we're still on part B, and we want to find the mean of X bar. And remember, that's just going to be our population mean, and it's 95.52377. And then the other part was to find the standard deviation for our X bar, and that's going to be the standard deviation, so 91.539124, and we're going to divide by the square root of 40 because that's our n. Work it from here. Okay, calculating my standard deviation for my X bar, I have 91.5394124 divided by the square root of 40, so I'm going to type that in my calculator, 91.5394124 divided by, and I type in the square root, the 40, parentheses, enter, and I get approximately 14.47. And what I want to do is write that out longer or store it on my calculator, so I have 14.473606 if I want to keep even more digits, which I think I do because look how many they have for the mean, so I'm going to just keep a bunch for the standard deviation as well. So that'll be my answer for the standard deviation. And then for part C, I want to know, let's go back up just a little bit, find the probability that X bar is less than 90. So first thing I want to know is what's my Z if my X bar is 90. So I'm going to take my X bar minus my mean for the sampling distribution, so 95.52377, divided by my standard deviation for the sampling distribution, so 14.473606, and then I'll calculate that, do 90 minus 95.52377, And of course I get negative 5.52377 divided by 14.473606. And I get, and remember z-scores, we only need 2 digits. So I'm going to round, it'll be negative 0.38. And there I'm pretty confident. Let's draw it, a quick diagram here. So I have my 0 here, and it looks like I have a negative 0.38. Oops. Which would be about there. And then what I'm looking for is less than 90, so it's going to be all those values to the left, which means if I want to calculate that area, that I'm going to have to do the probability of x bar is less than 90 is going to have to be the probability, or not the probability right there, but 0.5, right? .5 minus the probability that z equals 0.38. And remember, I just look up 0.38. I don't worry about that negative because it's not going to show up anyway. And 0, 1, 2, 3, so 0.1480. Yeah. Okay, so I get 0.1480 on my table lookup. So I have 0.5 minus that 0.1480, which gives me 0.352 for the probability that x bar is less than 90. And remember, we're talking about finding a large number of samples from our population that's described here, and we want to find what our probability that our mean number comes in less than 90. And remember, our actual mean is 95.52. So the probability that our mean, given the sample size of 40, comes in at less than 90 is going to be 0.3532.